So now we get to address that last little thing on the periodic table, the atomic mass, that goofy decimal on the periodic table that students will forever tell me is mass number, and it just isn't. So what is that goofy decimal on the periodic table? Well, it turns out we have to back up a little bit. We have to talk about this thing called an atomic mass unit, and that's because protons, neutrons, and electrons are very, 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 very small. It doesn't make sense to talk about them with grams and kilograms like we talk about everyday objects. One proton is about 1.66 times 10 to the negative 24th grams, and electrons are about a 2,000th of that, so even smaller. So we've got to use a different unit, and what we use is a unit called the atomic mass unit, because scientists are creative. The AMU is based on carbon-12. One atom of carbon-12 has a mass of exactly 12 atomic mass units. Carbon-12 was picked because it is fairly common. Now, protons have a mass of 1.0073 AMU and a charge of 1 plus. Neutrons have a little bit more mass, 1.0087 AMU and no charge. Usually we consider these to have a mass of 1 AMU. Occasionally we're going to get into the math where we do need to know that. And then of course electrons, 0.00055 atomic mass units and a charge of 1 minus. It takes about 1,800 electrons to get us the mass of one proton, which is incredible because they have exactly the opposite charge. So an electron and a proton will cancel each other in terms of charge, but their masses are considerably different. And then if you are paying extra special attention, you'll notice that this doesn't add up to 12. Right? If we take 6 times that plus 6 times that, we get 12 point something. We don't get 12. And that's because when the protons and the neutrons combine to form carbon, the strong nuclear force binds them together, and it makes it a very, very stable atom, and that increased stability means a loss of energy, and that energy actually used to be mass, and so turns out we can actually convert a little bit of mass into energy when nuclear reactions happen. We'll talk more about that when we talk about nuclear reactions. For now, it's okay that these masses don't work out. We do know where that mass goes, but it's outside of this discussion. So, atomic number, mass number, and atomic mass. These are three numbers that are forever getting messed up. Stop messing them up. So let's go through them one more time. Atomic number is the number of protons. Sometimes you'll see this gets the symbol Z. It is that whole number on the periodic table. It identifies the element we have. If we have 1 proton, we have hydrogen. If we have 12 protons, then we have element number 12, which is magnesium. It is also the number of electrons because atoms are neutral, and it is on the periodic table. It is always a whole number. In fact, the periodic table is arranged by atomic number. We have hydrogen over here, which is 1, and then we have helium over here, which is 2, and then lithium, which is 3, beryllium 4, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay? So that's how we arrange the periodic table, by atomic number, by the number of protons. That keeps going, the pattern repeats over and over. Then we have mass number, which is the number of protons plus the number of neutrons. This appears absolutely nowhere on the periodic table. The periodic table talks about general atoms. Mass number identifies specific isotopes. Most elements have atoms that exist as more than one isotope, so we need to be general on the periodic table, but we can talk about specific isotopes. So this is not printed on the periodic table of the elements, PTE. It's always a whole number because you can't have part of a proton, you can't have part of a neutron. Generally speaking, the atomic mass and the mass number should be similar. Atomic mass actually refers to the mass of the nucleus, the mass of the atom, whereas mass number refers to protons plus neutrons. They should be fairly similar, but they're not going to be exactly the same. Mass number is actually a count. Atomic number is actually a count. That's why these things say number. So mass number is a count of protons plus neutrons, and those only come one at a time. So it's always a whole number, and it's almost never on the periodic table. Then we finally get to atomic mass. This is a weighted average mass of all the isotopes of an element in atomic mass units. So, like I said, most atoms exist as more than one isotope, but they don't occur equally, which is why we have this weighted average. We're going to look more at that in just a minute. This is printed on the periodic table. It's almost never a whole number. In fact, it's never a whole number. There are a few of these that are printed on the periodic table as a whole number for man-made isotopes because we don't have a relative abundance of different isotopes. We barely have any at all. So this is that decimal on the bottom of the periodic table. When you're looking at hydrogen and it says 1 hydrogen 1.006, this is the weighted average of all the isotopes, the naturally occurring isotopes of the hydrogen atoms. So let's take a look at how we actually get that weighted average. Okay? So a weighted average gives weight to measures that occur more often. So if we are counting something and it occurs more often than something else, then it's going to drag the average around. So what I mean by that, if we take the average of 80 and 90, it's 85. We take 80 plus 90, we divide them by 2 because there were 2 measures, and we get 85. That's how we calculate an average. But if we had the average of 80, 80, 80, 80, and 90, that would be 80 plus 80 plus 80 plus 80 plus 90 all over 5. That is not 85, that's 82. You'll notice it's drugged down closer to the 80 because there's more of them. In fact, there's 5 measurements here and 4 of them are 80. That is to say 80% of our 80s, 80% of our measures are 80, 20% of our measures are 90. So we can actually shorthand this math and do it a faster way. We can sum the average. Okay, so the average is drugged closer to the 80 since the 80 is more abundant. And so mathematically, what we're going to do is we're going to add these by multiplying them by their percent abundance and then summing. So 80% of the measures were 80, 20% of the measures were 90. To find the weighted average, we multiply it by the percent abundance and sum. And what I mean by that is we take 80% times 80 plus 20% times 90. Of course, 80% is really 0.8. 20% is really 0.2, so 8 times 8 is 64, okay? Plus 2 times 9 is 18, and we get 82, which is exactly what we had up here. It's the same thing, but it shortcuts all this add, divide. And we can't actually count all of the atoms present in a sample, but we can say what percent of them are isotope 35 and isotope 37, which leads me to our last example. Chlorine exists as 2 isotopes, chlorine 35 and chlorine 37. 75.77% of chlorine is chlorine 35, and chlorine 35 has a mass of 34.968 atomic mass units. 24.23% of it is chlorine 37, which has a mass of 36.966 atomic mass units. You'll notice the mass is a little bit less than the mass number. This is mass number, this is mass number, this is atomic mass. Neither one of these numbers is printed on the periodic table, because if you were to actually go grab a sample of chlorine, if you had a bunch of chlorine gas floating around and you got some, you wouldn't get all of one or all of the other. About 75.77% of it would be this, and about 24.23% of it would be that. So if we actually want to talk about the atomic mass of chlorine, we want to talk about the average atomic mass of chlorine, but we want to make sure that we're taking into account percent abundance. So to get the atomic mass of chlorine, we're going to take 0.7577, that's this percent, times 34.968 plus 24.23, except we want to convert that to a decimal, not a percent, so 0.2423 times 36.966, and if we do the math on that, then we'll have the actual atomic mass printed on the periodic table for chlorine. Gets us 35.45 to 452 AMU, atomic mass units. That's the number that's printed on the periodic table, 35.45 atomic mass units. That's the average mass of a chlorine atom when we measure it in AMU.